Good morning, Year 10. This is Miss Teresa. Today we're going to discuss about diffraction. Our lesson objective for today is to describe how waves can undergo diffraction through a narrow gap, and success criteria. I can describe how wavelength and gap size affects diffraction through a gap, and I can describe how wavelength affects diffraction at an edge. First, we're going to review the physical quantities of a wave which changes when it undergoes reflection and refraction. Here's a table. For reflection, only amplitude changes, and for refraction, only frequency doesn't change. We will find out later which quantities change or do not change when waves undergo diffraction. But first, we're going to define diffraction. Diffraction is the wave phenomenon where waves bend around an obstacle and spread out. There is only one physical quantity that changes when waves undergo diffraction. That is amplitude. Amplitude decreases due to the spreading of energy with the increasing length of the waveforms. So, if we are going to compare the quantities that undergo changes during reflection, refraction, and diffraction, it would look like this. In reflection, amplitude changes. In refraction, only frequency doesn't change. And in diffraction, only amplitude changes. Here are the factors affecting the diffraction of waves. First is wavelength. Diffraction is more visible if the wavelength is larger. Say, we have a barrier here, and the wave approaching it has a large wavelength. As the wave passes through the gap, the spreading out of the wave is more noticeable, as well as the curving around the edges of the gap. To illustrate this, here will be the directions to the wave after passing through the gap. The speed, wavelength, and frequency of the wave does not change since it passes through the same medium. Therefore, the wave on the other side will look like this. Now you have to remember that the wavelength over here will be equal to the wavelength on the other side since it's the same medium that we're talking about. So roughly I'm representing it should be the same wavelength as the original wave on the other side. The second factor affecting diffraction of waves is the size of the gap. If the gap is smaller than the size of the wavelength, diffraction is more visible. To illustrate, here are the directions to be followed by the wave as it goes through the gap. The diffraction would look like this. Now you have to mind that the wavelength over here will be equal to the wavelength on the other side. Now, diffraction is the strongest or most visible if the gap is equal to the wavelength. To illustrate, here are the waves approaching the barrier with a gap, and here are the directions of the wave as it passes through the gap. Then, the diffracted waves will look like this. Still minding that the wavelength over here will be equal to the wavelength on the other side. As the gap gets bigger, diffraction gradually gets less noticeable until once the gap is much larger than the wavelength, the waves no longer spread out at all. To illustrate, here are the waves approaching the barrier. Here are the directions followed by the wave after going through the gap. Now the diffraction will look like this. Now we're going to draw the edges this way. Notice that the spreading is less noticeable. The wavelength of this will be equal to the wavelength on the other side. You have to be careful with that. Diffraction can also occur when waves pass an edge of a barrier. The waves curve as they pass the edge. Let's say that we have a barrier here which is half the size of our wavefronts. As the wave approaches the barrier, the directions will also change. Here's the direction of the wave as it passes the barrier. As you can see, here it will be just straight. The wavelength will be equal to the original wave, and the curving will occur this way around the edges. Now you have to remember that the wavelength speed, and frequency of the wave does not change as it goes through a gap, since the waves use the same medium. Only the amplitude decreases. Let's try to solve an example over here about diffraction. Figure shows the wavefronts of a plane wave approaching a gap in a barrier. The direction of the wave is given. And on figure, draw in the pattern of the waves after they have passed the gap. And this is 3 marks. So let's try and draw. So the answer simply will be this one. But why is it 3 marks? If you have drawn 3 concentric circles over here, or neat circles, okay, as your diffracted wave, then you'll be given 1 mark for that. Now the second mark will come from the wavelength over here. The wavelength of this should be equal to the wavelength of the original wave over here, so you have to be careful with that. You don't need to measure, you just have to do it by eye, and you have to draw your concentric circles neatly. And the third mark for that, so that's the second mark. The third mark for that will come from the center of the curvature of the arcs. So where's the center of your arcs? This will be the center of your arc here, at the center of your gap. So from there you will have your center of curvature of the 3 concentric circles. So that's 3 marks for your IGCSE type question. Now you're already familiar that the second question will be your work. You're going to write the answer on your notebooks, and you have to draw completely, and this is also 3 marks. So what have we learned today? We learned to describe how wavelength and gap size affects diffraction through a gap, and we described how wavelength affects diffraction at an edge. So this is Ms. Teresa once again, and I hope that you enjoyed this lesson. Have a nice day.